Glass and architecture, alternative origins and speculative futures. The material of glass, as we know it today, is changing. It can be derived from strange new sources, and it can also be created into products nearly unrecognizable from the building envelopes you are used to. When you think of glass, you might think of it as a rigid, compressible, and extremely brittle material. But today, glass can be flexible, ultra-thin, and subjected to unpredictable compressive forces. In this presentation, we will examine how glass may come from new origins and how the behavior of the material may change, subverting your expectations of the role of the material in the built environment. Here we see a diagram showcasing the tin bath float process. This is an exciting and relatively contemporary innovation that allows glass to become extremely flat as it cools. This process, while relatively new in the history of modern architecture, represents a more classical approach of looking at glass. The modernists viewed glass as a building material that should only act as a barrier to the elements, with little thought into energy and environmental demands. However, contemporary architects are now faced with demands for environmentally efficient glazing systems. Developments in glass coating technology have allowed for innovations in not only the optical design of glazing systems, but within the technology of heat transfer as well. Glass, once seen as a minimal, transparent barrier, now must control the flow of energy within a space. Therefore, glass has transcended its role as an agent of optics within design and now functions as a medium of energy transfer within a space. This research provides a closer look at the classical role of glass in architecture before analyzing its potential to yield new and exciting properties as a flat yet flexible material. Once perceived as a pristinely flat, transparent way to close a building envelope, flat glass has undergone a series of new experiments to manipulate its chemical makeup, as well as its structural behaviors. No longer having one method of production, nor a single structural behavior when applied to a building's skin, the material as we know it will soon be perceived differently. In this research, we will examine how the production of glass may change, as well as the expectations of the material within the built environment. Historically, for a glazing system to be energy efficient, it must only control the flow of energy that enters a space. This is typically solar energy and heat transfer from outside conditions. The amount of energy lost or gained by the glazing system can therefore be calculated. Although glazing systems can change the flow of energy into a space, glass alone does not provide adequate insulation to a space. Contemporary glazing units, however, often contain 2 or 3 layers of glass connected in one panelized system. The layers in between the panels are then filled with a low conductance gap, which invisibly reduces the thermal transfer. The gases used are usually argon or krypton, which have larger molecules than oxygen. When calculating the flow of energy, it can be concluded that heat transfer depends on various properties of the gas, some of which are density and viscosity. If researchers were to manipulate the production or structural behavior of the glass, its design capabilities and thermal performance would change. Low emissive or low E glass is a way for architects to cleverly circumvent the limitations of the material. A thin metallic oxide coating on a glass substrate reflects thermal energy from the sun without sacrificing transparency. These low E glass panels are typically done by 3 processes, either reflective dielectrics, transparent conductive oxides, or multi-layer metal dielectric stacks. These innovative methods of producing glass dramatically change how architects might close a building envelope. Innovations like these yield a wealth of schematic design possibilities that provide a building with the thermal resistance necessary by contemporary standards. Glass was once seen as a rigid, brittle, and completely transparent material, but today the material is subject to some fascinating new requirements. For such an invisible material, it possesses incredibly dynamic qualities. But where is this material sourced? Historically, glass is derived from the processing of quartz. Shown here, quartz is a crystalline igneous rock that occurs when magma cools. Research now shows that the material of glass can be sourced from potentially new and unexpected places, yet again subverting classical expectations of the material. Production of sodium silicate cullets, an important ingredient in the production of glass, have historically been derived through the processing of quartz. They are produced by the direct fusion of pure silica sand and soda ash at temperatures above 1100 degrees Celsius. Researchers have recently found that there are other non-quartz materials that can be used in the production of modern glass, yielding potentially innovative results in the field of glass design and structural behavior. For example, the production of sodium silicates can be performed by using trona, an evaporite mineral that possesses a large amount of sodium carbonate. Using X-ray diffraction, researchers were able to investigate the production of sodium silicate cullets from the trona powder. This is a process used to study the crystalline structure of a mineral by beaming X-rays into its structure. The diffraction and redirection of the X-ray beams onto the trona powder's molecular structure revealed that the sample of trona powder can be used instead of soda ash to produce sodium silicate cullets. By using an electron microscope, researchers found that crystals with different geometric shapes and dimensions were observed in the trona powder sample. When researchers melted down the trona quartz mixture, sodium silicate cullets were obtained successfully. In this study, the trona glass was most effective when melted at 1200 degrees Celsius, which is actually higher than the industry standard for glass cooling, usually at 1100 degrees Celsius. This means that trona glass could potentially be more effective at resisting heat transfer, although the literature in this regard is still rather narrow in volume. It is important that researchers explore the production capabilities of glass at its source, such as with trona and quartz. However, there are other ways to manipulate its behavior after it cools, by injecting other gases into its structure, for example. The behavior of volatiles, or evaporative gases, is important to the evolution of the Earth's geologic systems. Noble gases, such as helium, can be used for studying solubility in silicate melts. Helium, for example, has a strong effect on the structural behavior of silicate glass. This produces an unusually rigid behavior of glass. This injection of helium makes the glass much less compressible at high pressures. However, glass injected with hydrogen does not display this effect. It certainly begs some questions. Are there pressure mediums that make glass more compressible? And can gas injections make glass more flexible without impeding its pressure resistance? The results of these studies provide fascinating new information into the world of glass structure, production, and behavior. If glass can originate from different places and produce different behaviors, the material is likely to change right under our noses. As architecture becomes increasingly technologically flamboyant, the material will be placed under different technological expectations. In all aspects, the expectations of the performance of glass are changing. This phenomenological shift of expectations will not only change our understanding of polymorphic materials, but will change our understanding of transparency within architecture. These new technologies allow glass to take on different challenges in the world of schematic design, serving not only as a vessel of scientific thought, but one of a new literary mindset. Glass is no longer just an architectural medium. It acts as a temporal window, separating yourself from the built environment. Glass research allows the material to behave differently prior to classical expectations of the material as a static surface, providing new abilities to function in kinetic, flexible, and ultra-thin structures. As research continues on this fascinating behavior of this bizarre material, expect it to manifest unpredictably in the world of architectural and mediatic cultures. It certainly is an exciting time for glass research and innovation.